So this reaction that we have right here is electrophile Ischen substitution reaction, particularly a Friedel-Crafts acylation. So it's acylation because we have this acyl group with the that's attached to this halogen, and we're gonna essentially try to get this acyl group onto the benzene, and the benzene is also stable since it's aromatic. And to sort of make this reaction occur, we have to use this Lewis acid catalyst. So first step we want to do is to generate the electrophile. So take this acyl molecule and try to have it complex with this aluminum trichloride. Have these electrons get donated to this Lewis acid. And so it complexes with it, with the aluminum trichloride, and this bond right here is gonna, heterolysis is gonna occur with the electrons going to the leaving group, the chlorine. So then we generate this carbocation and aluminum, right? And so this is also, this intermediate right here is going to also be resonance stabilized by having this electron actually go here, make like a triple bond, because this is gonna satisfy the octet of the carbon here. And positive charge. And then we throw in our benzene. So also forgot to mention, yeah, like I said, this is, since completes octet, then this is the more important resonance contributor. But what we want to do with the electrons that are in the benzene, we're gonna donate that to the carbocation, and that's gonna results in, yeah, so this acyl group is attached to this cyclic compound, and the positive charge would be here, and this is resonance stabilized. So I can draw the resonance structures. This electron goes here, then that's going to move the positive charge here, acyl group over here, and the double bonds here, and then you just move this double bond here to move the positive charge over to the next carbon. So double bond, positive charge, whoops. Yummy. Okay, yeah, so yeah, the positive charge would be here. Yeah. Double bond here, double bond here, acyl group. And yeah, that's pretty much all the resonance structures there is to that. And then to satisfy that carbocation, so this first, yeah, so this part right here, when you added the acyl group to the benzene, this is the rate limiting step, since again this is stable. So you're breaking up aromaticity, so that's gonna have a higher energy barrier to overcome. But also, again, the intermediate that is developed here is going to be resonance stable as well. So one of the things that we do to satisfy this carbocation is there's a proton that's also attached here. So we're going to use this the electrons that are on a proton to recreate that double bond and return it back to being aromatic. So I'm gonna try it over here. Actually, yeah, we're actually taking this. I would prefer using this structure. Actually, let's see, can I use this structure here? Yeah, I could, yeah, do it like that as well from that end. Okay, and honestly, the base that's going to accept this proton, we can use any base, but I like to sort of return back to the original Lewis acid catalyst, since it's a catalyst, it's not gonna, it's in as a product, it's gonna get conserved and return to what it was. So I'm gonna do that. CO3, CO. Yeah, so the electrons, this proton, well, let's see. The electrons on this. So chlorine is going to take this proton, and these electrons are going to go back on the aluminum, and this bond right here, the electrons are going to return back to the ring, and then it's going to reestablish the very stable benzene. And this is our final product, as well as hydrochloric acid and our original aluminum trichloride, Lewis acid. And another things, this is going to be the major product, and what's awesome about the Friedel-Crafts acylation is that it's not an alkylation, and because in alkylation you have to consider rearranging the carbocation to make it more stable. So secondary carbocations are going to be more stable. So that's not something you have to worry about for acylation. So that's pretty much how I got the product in the end.